Welcome back to the explainer. Okay, so let's just jump right into this. If you recall, in our previous explainer, we completely broke down glycolysis. We took a single 6-carbon molecule of glucose, we split it right down the middle, and we walked away with 2 molecules of pyruvate, a tiny bit of ATP, and some NADH. But honestly, we are nowhere near finished extracting energy from that glucose, not by a long shot. What we're about to do today is, well, it's essentially a biochemical energy heist. We are going to take those pyruvate molecules, cross over into the mitochondria, systematically steal their carbons, and harvest all of their high-energy electrons. Now, before you start stressing out about memorizing some massive list of complicated enzyme names, just take a breath. Here's our game plan for today. We're going to progressively build this map together, step by step. We'll start with the big metabolic map, then we'll cross what's called the PDH bridge, take a look at the acetyl-CoA crossroads, spin the step-by-step TCA wheel, tally up our final energy yield, and finally, we'll make sense of the regulation logic. All right, section 1, the big metabolic map. Before we look at a single chemical reaction, we absolutely must establish where we are, where we came from, and where we're headed. Think of this as our big picture roadmap. So we started with glucose, right? Glycolysis happened out in the cytosol of the cell, which left us with pyruvate. Now that pyruvate enters a completely new territory, the mitochondria. From there, it's going to get converted into acetyl-CoA by an enzyme complex called PDH. That acetyl-CoA then enters the TCA cycle, which is basically a wheel that loads up electron carriers. And finally, those carriers are going to head straight to the electron transport chain to make a ton of ATP. That is the entire story in one glance. You always want to know exactly where you are on this map. Right now, we're at step 3, literally crossing the border into the mitochondria. Section 2, the PDH bridge. We have pyruvate, but the TCA cycle strictly requires acetyl-CoA, so we need a way to connect them. I like you to meet the Pyruvate Dehydrogenase Complex, which we almost always just shorten to PDH. Think of PDH as the absolutely vital, completely irreversible bridge linking glycolysis to the TCA cycle. Now, watch the carbon accounting here because it's crucial. Pyruvate enters the mitochondria containing 3 carbons, but the acetyl group we actually need to make, it only contains 2 carbons. So as our pyruvate passes through this massive PDH complex, we lose 1 carbon. It gets clipped off and released as carbon dioxide, which, by the way, is exactly why you exhale CO2. At the exact same time, a molecule called NAD+ swoops in, picks up a pair of high-energy electrons, and becomes NADH. Finally, coenzyme A attaches to our remaining 2 carbons, and the result, we have our 2-carbon acetyl-CoA. So just to recap that, 3 carbons went in, 2 carbons came out, 1 CO2 was lost, and 1 NADH was generated. But wait a second, you've got to remember our origins here. Glycolysis split 1 single glucose into 2 pyruvates. Because of that, everything we just walked through across this PDH bridge actually happens twice for every original glucose molecule. So 2 pyruvates become 2 acetyl-CoAs, we release 2 carbon dioxide molecules, and we produce 2 NADH molecules. Definitely keep that in your back pocket for later. Now, because PDH is a one-way gate, it is completely irreversible, the cell regulates it brilliantly. You really don't need to strictly memorize this. Just follow the logic. If your levels of ATP, NADH, and acetyl-CoA are all super high, what is the cell essentially telling us? It's saying, hey, we have plenty of energy. So an enzyme called PDH kinase steps in and puts the brake on by phosphorylating PDH, completely turning it off. Why shove more fuel through the gate when the gas tank is full? But look at the contrast. Say you suddenly start sprinting. Your ADP rises. Energy demand shoots up. In that working skeletal muscle, calcium literally floods the cell. That calcium acts as an emergency signal to activate an enzyme called PDH phosphatase, which removes the brake, turning PDH back on. The gate flies open to meet the new energy demand. It's so elegant. Okay, moving to section 3, acetyl-CoA crossroads. We've officially crossed the bridge, but before we spin the wheel, we really need to respect the molecule we just created. You see, acetyl-CoA isn't just the end product of our PDH bridge. It is a massive, bustling intersection on the metabolic map. We got here today by burning carbohydrates, but if you were burning fatty acids, those would also break down into acetyl-CoA. Even portions of amino acid metabolism feed directly into acetyl-CoA. It's the ultimate convergence point where all these different fuels meet up before entering the central energy system. Section 4, the step-by-step TCA wheel. You might know it as the citric acid cycle or the Krebs cycle, but whatever you call it, it all happens right here in the mitochondrial matrix. Before we throw any complicated enzyme names at you, let's just focus on the basic math of this wheel. It's super simple. Waiting at the top of the cycle is a 4-carbon molecule called oxaloacetate. Our brand new 2-carbon acetyl-CoA arrives. 4 plus 2 gives us 6, so we begin the cycle with a 6-carbon molecule. And as we travel around this wheel, we're going to progressively remove carbons as CO2, harvest a bunch of high-energy electrons, and eventually regenerate that exact same 4-carbon oxaloacetate we started with. 2 carbons go in, carbon dioxide comes out, and the wheel spins again. The absolute most crucial point to understand is this. The TCS cycle's main job is not making massive amounts of ATP directly. Its main job is loading electron carriers. I love thinking of NADH and FADH₂ as the cell's energy delivery trucks. As the carbons are oxidized and systematically removed, the cycle harvests those high-energy electrons and packs them into these trucks, and those trucks are bound directly for the electron transport chain. Okay, let's actually build the cycle step by step. Step 1. An enzyme called citrate synthase joins our 4-carbon oxaloacetate and our 2-carbon acetyl-CoA to make the 6-carbon molecule citrate. We are officially in the cycle. Step 2. An enzyme named aquinatase slightly rearranges that citrate into isocitrate. We still have 6 carbons, we're just repositioning things. But step 3, this is a major control point. The enzyme isocitrate dehydrogenase steps up. Dehydrogenase is a huge clue here. It means we are stripping away hydrogens and electrons. So here, we lose our first carbon as CO2, and NAD+ picks up our first batch of electrons to become NADH. We just loaded our first delivery truck. Let's just pause and anchor ourselves for a second. Because we just lost a carbon dioxide molecule at the isocitrate dehydrogenase step, our carbon count has officially dropped from 6 down to 5. We now have a 5-carbon molecule called α-Ketoglutarate. Continuing around the wheel, that 5-carbon α-Ketoglutarate meets the enzyme α-Ketoglutarate dehydrogenase. Once again, we lose a carbon as CO2 and we load yet another NADH truck. Now we're down to 4 carbons in the form of Succinyl-CoA. Next, Succinyl-CoA synthetase converts it into Succinate. And this step brilliantly illustrates a rare moment of what we call substrate-level phosphorylation. Right here, we generate a GTP molecule, which is energetically equivalent to ATP. We literally just made direct, usable energy without even needing the electron transport chain. Next up, succinate becomes fumarate via the enzyme succinate dehydrogenase. And we load a slightly different truck this time, FADH₂. But I really want you to pause and think about this definition because it's mind-blowing. Succinate dehydrogenase is an incredible dual agent. It's an enzyme participating right here in the TCA cycle, but it is also complex 2 of the electron transport chain. It's literally embedded in the mitochondrial membrane. This is a physical, tangible connection bridging the TCA cycle directly into the next major pathway we'll be studying. It is metabolic architecture at its absolute finest. Let's finish up the wheel and bring it all the way home. Fumarate becomes malate using the enzyme fumarase. Finally, malate dehydrogenase converts malate back into oxaloacetate, and in the process, it loads one final NADH truck. And look exactly where we ended up. Oxaloacetate, the exact same 4-carbon molecule we started with at the very top. The cycle is closed, the starting material is entirely regenerated, and it's perfectly primed and waiting to accept the next incoming acetyl-CoA. Section 5, the final energy yield. We just pulled off the heist, so let's zoom out and tally up exactly what we stole. Let's look at the final accounting. For every single turn of the cycle, meaning 1 acetyl-CoA going through, we yielded 3 NADH, 1 FADH₂, 1 GTP, and 2 CO2 molecules. But remember our golden rule. 1 original molecule of glucose gave us 2 pyruvates, which gave us 2 acetyl-CoAs. Therefore, per glucose, the wheel actually spins twice. That doubles our entire loop to 6 NADH, 2 FADH₂, 2 GTP, and 4 CO2. And don't forget the PDH bridge we crossed earlier. That gave us 2 additional NADH as well. We are accumulating a massive, massive fleet of loaded delivery trucks. Section 6, regulation logic. With a metabolic pathway this unbelievably powerful, the cell absolutely has to control the flux so the wheel doesn't just spin wildly out of control. Once again, please don't just blindly memorize this, follow the logic. The major internal control points here are isocitrate dehydrogenase and α-Ketoglutarate dehydrogenase. If ATP and NADH are high, the cell basically says, okay guys, we're full, and those enzymes slow down the traffic. If there's a buildup of products like Succinyl-CoA, it acts as a negative feedback loop to pump the brakes. Conversely, if ADP is high or if calcium is surging because you're contracting your muscles, it's a blaring emergency signal for more energy. The enzymes speed up, opening up the road for much faster metabolic flow. Now, the TCA wheel isn't spinning in an isolated vacuum. It's a really busy intersection. Sometimes intermediate molecules get pulled out of the cycle to help make things like amino acids or new glucose. Well, if we lose our 4-carbon oxaloacetate to another pathway, the 2-carbon acetyl-CoA suddenly has nothing to attach to. The whole wheel grinds to a halt. Fortunately, an enzyme called pyruvate carboxylase can take pyruvate and convert it directly into oxaloacetate to completely restock the cycle. Pyruvate doesn't always have to become acetyl-CoA. It can also act as the crucial backup generator to make sure the wheel keeps spinning. Let's put the whole picture together from the top down. You've just completely mastered the narrative of carbon oxidation. We started with 1 glucose that broke down into 2 pyruvates. They crossed the irreversible PDH bridge to become 2 acetyl-CoA molecules. Those 2 molecules entered the mitochondria, joined up with oxaloacetate, and spun the TCA wheel twice. We successfully removed carbons as CO₂, regenerated our starting oxaloacetate, and most importantly, we harvested a massive amount of high-energy electrons. The heist is a success. But honestly, this leaves us with a giant, lingering question. What on earth are we supposed to do with all of these loaded NADH and FADH₂ delivery trucks? I mean, we've collected them from glycolysis, from the PDH bridge, and a huge amount from the TCA cycle. Well, they are all about to merge onto the final metabolic highway. They are heading straight to the inner mitochondrial membrane, where the electron transport chain is going to use them to crank out massive, life-sustaining amounts of ATP. And that's exactly where we're heading in our next explainer. Keep learning, stay focused, and I'll see you there.